Excuse me, we're going to start. It's a long session and we're going to be going through dinner if we're not careful. This is to welcome you to our union session on the consequences of this unusual sunspot minimum. We're going to be hearing papers on various aspects of the minimum, including luminosity and history and energetic particles right to the present. So let me call the first paper, which is Solar Magnetic Field and Irradiance, How Unusual is the Current Minimum, given by Solanki. As I said, we'll let you know after when you have 3 minutes to go. It's 15 minutes.
Okay. Where do I, this is the right or this one? Okay. So, good afternoon, ladies and gentlemen. Let me begin by asking the question, why should we give a damn? Why should we study the current minimum? What do we hope to learn? Now, there are a number of things that we hope to learn from that. And the first is, if we want to understand and if we want to find out if the sun influences the Earth's climate in any significant way, then we need to know what the solar irradiance has been doing in the past, and not just its cyclic variation, but also if there is a secular trend and by how much it has changed between, for example, the Maunder minimum and now. If you want to understand what is causing any long-term change of the irradiance, we need to know what the magnetic field has been doing, if that shows any secular trends. The structure of the field and its evolution, its interaction with motions in the sun's interior or surface, for example with convection, drives not just the irradiance, but many other things also: solar activity, the structure, temperature of the corona, and even properties of the heliosphere. As a little side effect, or as a big side effect, the present minimum will provide us, or hopefully will provide us, information, new ways of testing dynamo theory and trying to understand how the magnetic field is generated and what causes its evolution. And as a final side effect, we have learned something also about the sociology of solar physics, of how mature our science is. One of the definitions of a maturity of a science is that one can make predictions. And to my knowledge, at least, there was no serious prediction about what this minimum was like, which puts us in about the same ballpark as economists. Now, that's a pretty worrisome thought, I think. So let's move ahead to the question, how unusual is the present minimum? And I'm just going to talk about global properties here. Right? There are many details which are different, but let's just look at the big picture, so to say. What you see on this diagram is, in the last 45 years, the heliospheric magnetic flux, which is the thick blue line. And if you follow it, you'll find that in the last couple of years, it's been lower than at any time in the last 45 years, which is basically the whole space age. That's the period of time where we could measure it. And so definitely unusual, but that's not a very long period of time. If you want to go much further back, then you need another proxy, and sunspots are a good one. We have 400 years of that. And if you look at the number of sunspots, that's the shading, the light blue shading in this diagram, also for the same period of time, the last 4 cycles. In the present minimum, we have had 762 spotless days as of December 1st. And this is way more than any of the previous 8 minima before that. It's more than twice the average number that we have had in these previous 8 minima. So yes, indeed, the current minimum is unusual. However, if you go further back in time, the 4 minima before that, let's say the second half of the 19th century, this was not unusual at all. you have had, in those 4 minima, you've had similar numbers or even more spotless days during a given minimum. So it's an unusual minimum, yes, but it's not an unusually unusual minimum. If we go closer to the sun, then we expect the heliospheric field to be driven basically by the magnetic field at the poles of the sun. And this is a diagram that you have seen if you were in the session on on Monday afternoon, like the previous one as well. What's shown here is as a function of time from 1976 till now, the polar magnetic field of the sun as measured by Wilcox Solar Observatory, and the minima are given by these extrema, right? The horizontal line in the middle is 0, and you see that at the current minimum, the polar field is only about half as strong as it was in the 3 previous minima. So again, unusual, but again, not a very long period of time that we are comparing with. And this is consistent. Having it about half as strong in the polar field is very much consistent with having a heliospheric field, which is also roughly half as strong as it was in the previous few minima. Let's move on to the solar irradiance. The total solar irradiance, that means the brightness of the sun as a whole integrated over all wavelengths. Now that's a much more tricky thing to measure, and it's also difficult for a longer period of time because you don't have measurements from the same instrument, and you have to put them together. And depending who does that, they get somewhat different results. So what I'm showing you here is a composite put together by Klaus Fröhlich, the Davos composite. And you can see that in the period of time, since measurements started in 1978, there have been 3 cycles roughly. You see the 3 maxima, you see the 3 minima. The first 2 minima were at about the same level. The present minimum is lower by about 0.28 watts per square meter compared to the others. Just for comparison, the amplitude of the solar cycle in the total solar irradiance is about 1 watt per square centimeter. So again, a new development there compared to what we had in the previous couple of cycles. Finally, let's consider the total magnetic flux of the sun integrated over the whole solar disk, or just looking at the center of the solar disk. And we find that in the present minimum, the amount of solar flux, magnetic flux, is only about 60% what it was in the minimum of 1996-97, even if you exclude the poles. So it's not just this open flux at the poles which has changed, but it's actually the very structure of the magnetic field. In the quiet sun, the amount of field you have in the network is considerably lower now than it was before. Now, this fits in quite well also with the fact that the irradiance is lower, because using this lower average magnetic flux that we have on the sun also implies that there will be a reduced total solar irradiance, so they fit together very well, and that again confirms previous results that the total solar irradiance variations are indeed caused by the magnetic field at the solar surface, which contradicts a recent paper by Klaus Fröhlich. But he didn't actually compare the magnetic field with the irradiance. He compared the magnesium index with the irradiance and found that they diverge recently. But if you look at the magnetic field itself, you find that it goes very well with the irradiance. Now, the important thing, the thing I find most exciting from all of this, is that for the first time, we are seeing a secular change in very basic parameters of the sun, in the total magnetic flux, in the open magnetic flux, in the irradiance. This is something we have been discussing for a decade or 2 even, but now we actually have direct measurements showing us that. That, I think, is the most exciting thing to have come out of this minimum. Now, can we explain such secular change? Yes, indeed, there is a mechanism, and it's based on having overlapping solar cycles. Okay? So if you look at the upper diagram for a moment, you see the individual dashed green curves as a function of time would be the amount of magnetic flux which is emerging at the solar surface. And if two solar cycles overlap in the sense that flux is still emerging in the old cycle while it has started emerging in the new one, the magnetic flux will never drop to zero between them. So you'll get a minimum where you have a certain amount of flux, and depending on whether the next cycle is strong or weak, whether it peaks early or late, the level at which you will have magnetic flux in the minima will be higher or lower. And you can get secular variations of this type. There are different variants of this, but that's the basic idea, okay? Overlapping cycles. You can then use this, make a simple model, put this in a few differential equations, and starting from sunspot number, we had shown already a number of years ago that you can produce secular variations in the total, in the open flux, and in the irradiance as well. Now, very recently, in a paper together with Luis Vieira, we have improved on the model. We have extended it by distinguishing between rapidly and slowly decaying flux. It doesn't change anything in the very basics, but what it does is it improves the correspondence with the observations. And just an example, you see in the lower diagram the total magnetic flux, the total time series that is available to us starting in the 1960s with Mount Wilson and then Wilcox and Kitt Peak coming in as well. So these are the colored symbols. Those are the measurements. The black line is what the model gives. And in particular, if you look at the last few years, the model agrees very well with the data, even in this time when the flux has fallen to lower values than we had before. And the nice thing is that we did not use this period of time to constrain the model's free parameters, right? We stopped there where that vertical blue line is at around 2001. So the rest is just what comes out of the model, and it agrees quite well with the data. You can do the same thing for the open flux, which is given in the upper diagram, where we are comparing the model, which is the blue curve, I think, with the reconstructions of the open flux by Mike Lockwood and co-workers, which is the black curve. In the lower diagram is the comparison with the irradiance. In both cases, where the open flux has fallen low and the irradiance has gone down, the model is going along with the data. Again, we didn't use this most recent period to constrain the model. Now, if you listen carefully 2 slides ago, you will be wondering now, what did they do about cycle 24? Because remember, we are talking of overlapping cycles. What we did about cycle 24, because we don't know how strong it will be, we just assumed there is no cycle 24. So there is no cycle 24 in this model, and the model then reproduces the data extremely well. Does that mean we are going to go into a Maunder minimum-like event? I don't think so. This is not the most precise way to make predictions for the next cycle. Okay? But what it is suggesting to us, I'm not saying it's telling us, what's suggesting to us is that cycle 24 will either be weak, or it will peak late, or some combination of these. Okay? Now, if we assume that the model is not doing too badly, since it does reproduce the data quite well, we can then compare where we are compared to the period of the Maunder minimum. We can go back all the way where we have sunspot data 400 years, or 300 years in this case. I've just plotted since the end of the Maunder minimum. And you see, yes, the flux has fallen quite a way, but it is nowhere near there where, at least according to the model, it would be in a Maunder minimum-like state. We haven't even reached, if you look at the lower diagram, it shows the open flux. We haven't even reached the levels where, according to the model, we would have been in the Dalton minimum, around 1800, when there were a few very weak cycles, and the open flux and also the total flux were very low. So basically, we are at the level of around the 19th century, which is interesting because also the minimum as far as the sunspots are concerned is also like the minima that we had during the 19th century. Okay, we come to the conclusions. The current minimum has demonstrated that both the magnetic field, the total flux, the open flux, whatever, and the irradiance display secular variations. I think this is an extremely important result. This is something that we have been discussing for years, for decades. There were indirect indications for that. Now, finally, we have direct proof, direct measurements that this is the case. What I'm quite happy and relieved about is that even the simple models that we have constructed for the evolution of the magnetic flux reproduce the data relatively well, including this unusual present minimum that we have, although this was nothing that we tweaked the model to do. It came out naturally. And finally, the behavior of the present minimum suggests that the sun is returning to an activity level compared to what we had in the 19th century. Or, even beyond that, not just the 19th century, but actually during most of the Holocene. The diagram you see here is the number of sunspots, or the sunspot number, reconstructed from carbon-14 data over the last 7,000 years. We have put in two different bars. The blue one at the bottom, whenever the sunspot number fell below that value, we said the sun is now in a grand minimum state. You see there were a number of these grand minima, but there have also been times when the sunspot number was very high over those red values, when there were grand maxima. And the last 50, 60 years has definitely been a grand maximum, and one of the strongest ones we have had. And it looks like the sun is now leaving that grand maximum. Where it's going to, I don't know. I think we have really exciting times ahead of us. Thank you very much.
Please repeat the question. Yeah, sure. Yes, Gerhard.
If in the course of next year the magnetic flux would go down to the level of the normal minimum, what would be your prediction for the next solar cycle?
Oh, I'm not better than so the question was, if in the next year the flux were to go down to the level of the Maunder minimum, what would be my prediction for the next cycle? Oh, I don't think I would dare to make a prediction. I'm definitely not as good as the economists are.
Any other questions? Yes.
Okay. You see from the graph that there is no, yes, I'm repeating the question, that there is no grand maximum around 1,000? Yes, well, yeah, you have seen correct. There is no grand maximum around 1,000 according to this data set, right? This is one data set of carbon-14 which was put together by a whole bunch of groups, but there are also beryllium data which don't look exactly the same. So you will find, differences in detail, but you will still see the same picture that you have grand maxima and grand minima, and the last 50, 60 years is a grand maximum. There was one more there.
One over there. I'm sorry.
Does this help us to evaluate which reconstructions of TSI make the most sense or look most like reality?
The question is if this diagram here help. No?
You're not the diagram, but your discussion of what we've learned from the new metal.
Okay. The question is, there is a debate about what the TSI composites. There are three different ones which differ from each other, and the question was if the current minimum is helping to distinguish between them. Well, it helps to distinguish between them only if you believe that the model has anything to do with reality. If it does, then yes, indeed, it does support the Davos composite, but that's all I want to say. I don't want to say the model is better than the data.
giving a talk, The Effects of Low Solar Activity upon the Cosmic Radiation of the Interplanetary Magnetic Field over the last 10,000 years and implications for the future. This is an invited talk.
Thank you, Randy. Ladies and gentlemen, it's my pleasure to be here.
We'll let you know in a few minutes.
Say again?
We'll let you know after 15 minutes.
We'll give you a warning after 15 minutes.
Yes. Professor Solanki has given us a good introduction. The Sun is currently doing something which we haven't seen it do before. My job is to talk about the extent to which historical records will tell us whether it has done it before, how often, and what we might learn to expect. Where's the... Oh, thank you.
I'll change it for you.
Okay, the outline of the paper is before you. It will be based on the paleocosmic ray record, which is based on a number of cosmogenic nuclides. I will explain that a little bit because in the last 10 years, the whole story of the cosmogenic nuclides has changed very greatly. And I want you to just understand where we are now in that. I will look at the last 1100 years to get a feel for what we might expect. I'll use 10,000 years to get statistics, and then we'll talk about a few other issues. Next, please. Very briefly, the data is obtained from a process which happened back in the past when a cosmic ray whacked into the top of the atmosphere. It produced a cascade of protons and neutrons. These interacted with oxygen and nitrogen and argon atoms. Spallation processes then were archived in ice. There was a parallel path through carbon-14, which I will mention briefly a little later. There's another process entirely whereby very intense cosmic radiation from solar flares can produce nitrates in the polar atmosphere, which are also sequestered in ice cores. And that gives us a method of looking at the paleocosmic ray solar flare occurrence. Next, please. Let me just explain where we have come from in the last 10 years in respect of the paleocosmic ray data. 10 years ago, we knew that there were variations in the carbon-14 and the beryllium-10, but we couldn't relate them to our experimental measurements with neutron monitors or with satellites. In that 10 years, we've come forward in a number of directions. First of all, the satellite measurements have given us a much better understanding of the manner in which the solar activity changes the spectrum of the cosmic rays. We have used very large mathematical models to simulate the nucleonic cascade in the atmosphere, which produces protons and neutrons, and then have used nuclear cross-sections to estimate the manner in which production of the cosmogenic nuclides depends on energy. In other words, we are developing the relationship between incoming flux and the production of the nuclides. There's one major issue still remaining, which is then how those nuclides, which are produced both in the stratosphere and the troposphere, are sequestered in ice. Large global circulation models in the last several years have answered those questions. So we now can quite accurately intercalibrate the paleocosmic ray records with the modern era, and that's what I will be doing now. Next, please. But just to give you an idea of what this is telling us, there we have the relative response of the neutron monitors, which are well known, which you can see have peak energy response at about 5 GeV. The beryllium-10 that I will be using in a moment has a peak response in the vicinity of 1 GeV, sort of midway between the neutron monitors and the higher energy spacecraft measurements on IMP and such spacecraft. So we can see now how the beryllium-10 and the carbon-14 are more sensitive to long and short-term changes than neutron monitors. More important, we have the interconversion calibrations, which I now use. Next, please. Just very quickly, of course, to define the terms which you all probably know, the solar grand minima are occurrences such as occurred during the Maunder minima, 1650 to 1715, the Dalton and the Gleisberg minimum of 1900. Next, please. So now let's look at what the paleocosmic rays were doing during those minima. We're going to look primarily at the minima. And look at the one for the Maunder minimum. You can see that the cosmic ray flux, look at the South Pole in the middle there. I better have the, where's the pointer? Oh, great, thanks. Yes. Okay. Yeah, sorry. Okay. Looking at the middle panel here, that from the South Pole you can see that on the far right the current intensity is about half of what it was during the Maunder minimum. We can see that during the Dalton and the Maunder and also 1900 the intensity was considerably higher. That is, the amount of beryllium-10 or the cosmic rays were considerably higher, and you can see there were similar events earlier called the Wolf and the Oort minima, which we know were periods of low solar activity because there were low aurora recorded in the old history records of Europe. Now, those data are averaged over 22 years, so they've averaged over the 11-year cycle. Let's have the next one, please, Joe. Here we now have the paleocosmic ray data for the last 600 years, where we can see the 11-year variation. You can see there is substantial variation through the whole period. You can see yet again that the intensity was high during the Maunder and so on. The question I want to look at now is, to what extent was the Sun still varying the cosmic radiation flux during the big minima? That is, was there still a varying magnetic field? Was there still varying modulation? Next slide, please. Now, this is the Spura minimum, which is the most profound minimum we've had in the last 1,000 years. It lasted about 100 years, 120, and you can see that the modulation, the variation, continued through that whole period. It was a quite substantial variation. We, in the cosmic ray community, have something called a modulation potential, which is not a very good measurement, but it's a parameter anyhow that gives you something. And it was a roughly 200 MeV modulation function change. This was a substantial variation. It tells us that the magnetic fields were varying substantially, certainly on a 22-year periodicity, but the 11-year was there as well. Next slide, please. So now we know that the cosmic ray intensity was high during periods of low solar activity. We have seen 5 of them in the last 1,000 years. Let's now look at the last 10,000 years. Here we have at the top the beryllium-10 production record, at the bottom the carbon-14. There are differences. There's an important issue here that the manner in which they are stored, one in ice and the other in trees, are quite different, and the noise terms in each are different from each other. So by combining them, getting the production signal out of them, we can get rid of most of the noise, and that's what we do now. I do point out that the glaciologists put time the wrong way for us. And so note here that it is time before present. A long time ago was on the right, now is on the left. And just to remind you of that, I have time on the time arrow henceforth. So, combining these data, next slide please. This is then the 10,000 year cosmic ray record. There's the spur minimum. The core did not have the maunder in it. It didn't start till it was down about 1500 AD. The most important thing to notice, I think, is that there are about 22 maunder minimum or spur minimum type events. That is, the Sun does this frequently. And these are the big ones. There are smaller ones down in this graphs here. The red line is at the present situation, and just for reference, these low values through here are because the geomagnetic moment was about 20% higher then than now. So that's showing us both what the cosmic rays were doing, but just as a check, you can see what the geomagnetic field was doing. Next, please. Now I'm going to change quickly to, very briefly, the question of solar energetic particle events. The paleocosmic ray record does include such signals. The largest one known is the Carrington event up at the top. During the Gleisberg cycle, and the Gleisberg minimum, that's one of the low grand minima, it's not quite a grand minima, but around about 1900, there is a burst of very large solar energetic particle events. Some, including a couple that are not on there, there were some 8 large events. One of them, the second largest in the whole record, and so here we have very substantial production by the Sun. If we go back to the Dalton minimum, we find just the same bunching of production of solar energetic particles. And there are theories about this. I won't go into it now because my time's running out, so we'll move on to the next one. Using Parker's transport equation, we can make approximations, I stress approximations, as to what the magnetic field at the orbit Earth was doing. And here's the estimate for the last 600 years, a steadily ramping up intensity with 11-year modulation on top of it, going up to the 5.2 at solar minimum that we've observed until recently, and of course it's now down to where the second arrow is. So this would suggest that the magnetic field is beginning to reverse downwards. Next, please. If we look at the last 10,000 years, this is an estimate by Friedenstein-Helber for that period. Note time is going the right way this time. We can see the grand minima. The one I want to point to is the bottom curve, which is showing us that there's a long-term variation of period 2,200 years. This was detected by Chuck Sonnet 30 years ago. But this is the first time we've ever known what its phase is. You can see here that it was a minimum, and in fact it is defined by the bunches of grand minima that occur. And so the maunder minimum, the spur minimum, cause that low value there. This tells us that that cycle is probably a quarter of its way through to the next minimum in 2,000 years' time, which is suggesting, as I'll show in a minute, that we certainly are not going to have another maunder minimum. Next slide, please. So let us summarise what our historic record has told us as to what's happening now. First of all, it suggests to us that reductions in solar activity, such as are occurring in this minimum, have occurred quite frequently in the past. Very large reductions, such as the Maunder or Spera minimum, roughly once every 500 years, but a bit clumped. The smaller ones, once every 100. And so on. You can see that the cosmic radiation fluxes are high. The durations of these events are 1 to 5 solar cycles and so on. And I won't dwell on that anymore because to allow some time. But finally, and I stress that the next slide should not, my co-authors should not be blamed for the next slide. This is me and me only, saying if I look at the data, if I look at the paleocosmic ray records, what do I say is about to happen? So there's the prediction through looking at the paleocosmic ray record. A Maunder minimum is most unlikely because of the Halstead periodicity that I mentioned. The Dalton minimum is my bet, because what I didn't point out was that there's a periodicity in the records. There's a very clear and quite fixed 208-year periodicity at the de Vries cycle. And this, to me, we're just about 208 years from the Dalton. The event like 1900 is possible, and a non-event is, by my counting, not likely. Thank you. The next one. And that is thank you.
Yes, we have time for a couple of questions.